You might be sick of the word acceleration, in which case you're in luck because the next version of the paradox is the inertial version, which doesn't involve it at all. But how can Mary return to Earth without accelerating? Well, unfortunately she can't, so in this version it'll have to be her robotic clone, RCM4, that takes her place back on Earth. Specifically, Mary leaves Earth traveling at 0.6 c, with the same destination, a star that's 3 light years away. The moment she arrives, she transfers some data to RCM4, who travels to Earth, again at 0.6 c. Just like before, we can avoid acceleration by having Mary and RCM4 already in motion and simply passing by Earth. But unlike before, we can also avoid the turnaround by having Mary and RCM4 pass the star at the same time, with the data transfer occurring in that exact moment. The data transfer includes an age variable. Basically, however old Mary is at that moment is what RCM4 will set its own age as, with it then increasing as normal with the passage of time. The setup is a bit complicated, but it gives a proxy for Mary's age upon their reunion without actually having her turn around. RCM4's age upon reaching the Earth is simply the amount it aged during the return trip plus the amount Mary aged on the outbound trip plus 20. Since there's no turnaround, it seems like we get a contradiction again. In Botan's reference frame, she ages 5 years on the outbound trip while Mary ages 4, and another 5 on the return trip while RCM4 ages 4, making their ages 30 and 28. But in Mary's reference frame, Botan is moving at 0.6 c and only ages 3.2 years on the outbound trip while Mary ages 4. Then on the return trip, RCM4 also sees Botan moving. It's in the opposite direction, but still 0.6 c, and therefore Botan again only ages 3.2 years while RCM4 ages 4. If we combine these, we get their ages being 26.4 and 28, which is a contradiction. But here's the thing. Even though Mary and RCM4 are in the same place during the data transfer, they still have different velocities, making them different reference frames. Now we know that in Mary's reference frame, Botan is exactly 23.2 at the time the transfer occurs. But these two events happen light years apart, meaning relativity of simultaneity kicks in. And so just because they're simultaneous in Mary's reference frame does not mean they're simultaneous in RCM4's reference frame, despite the fact that the two observers are in the same place at that time. It's not the location of the observers that affects simultaneity, it's the location of the events. It might seem like an issue to have Mary and RCM4 see Botan at different ages when they themselves are in the same place at the same time. But remember, the speed of light is finite, so you don't see things in real time. Instead, you see them as they were when the light was emitted. You don't see things in real time. Instead, you see them as they were when the light was emitted. In the example, the light they received during the transfer will show Botan at age 22, so they will both agree that Botan was 22 when she sent the light they're currently receiving, even though they disagree on when that light was sent out. So what does this mean for the paradox? Well, the calculation that said Botan is 26.4 was based on the assumption that her age at the moment of transfer remains constant after you change reference frames. But now that we know that's not true, the calculation holds no weight. In reality, we can't calculate Botan's age by doing half in one reference frame and half in another. Instead, we have to use the same reference frame the whole time. We already did that once with Botan's own reference frame, but we still have 2 more to try it on, namely Mary's and RCM4's. We'll start with Mary's reference frame. Botan's velocity is simply 0.6 c to the left, since that's how fast she observed Mary to be moving. The same thing applies to the star, and due to this, the distance from the star to Earth is contracted to 2.4 light years. So, at time 0, Mary and Botan both start at position 0, with the star 2.4 light years to the right. But since Botan and the star are moving left, after 4 years it's the star at position 0, with Botan 2.4 light years to the left. It's at this point that the data transfer occurs, and we start tracking RCM4. You might think it would take another 4 years for RCM4 to reach Botan, but that would only be true if velocity is added. Instead, we have to calculate RCM4's velocity using the formula from episode 6. Mary sees Botan move at 0.6 c, and Botan sees RCM4 move at 0.6 c in the same direction. Therefore, Mary will see RCM4 move at 15/17 of c, which is about 0.88 c. This effect basically nerfs RCM4's velocity, meaning it takes a lot longer to catch up. By forming a system of equations, we can see that it'll actually take a full 8.5 years, meaning they finally meet at time t equals 12.5. But it's not the time itself that matters, but instead the ages of Botan and RCM4. Botan maintains a constant speed of 0.6c the whole time, in which case alpha is 0.8. 0.8 times 12.5 is 10, so Botan only ages 10 years and ends up being 30, just like before. Meanwhile, RCM4 is 24 at t equals 4 due to the data transfer, but for the return trip, its velocity is 15/17 of c, in which case the alpha factor is only 8/17. So in those 8.5 years, RCM4 only ages 8.5 times 8/17, which is 4 years, making it 28 by the end, again just like before. So to recap a bit, it seemed like we would get a contradiction due to Botan only aging 3.2 years during the outbound trip, but although this is true, when we continue in the same reference frame, the return trip takes much longer due to how velocities combine. This gives enough time for Botan to age the full amount, while RCM4 moves even faster than Botan, and therefore ages much slower, and still only 4 years in that time. And for added context, here's an abridged form to better show the calculations. So, even after switching to Mary's reference frame, we still get the same outcome. The moment they meet, Botan is 30 and RCM4 is 28. But what if we use RCM4's reference frame the whole time? Well, it's actually very similar to before, just in reverse. This time, it's the outbound trip that takes 8.5 years, and the return trip that takes 4. Mary still ages 4 years, followed by RCM4 aging 4 more, totaling 28. Meanwhile, Botan ages 6.8 years on the outbound trip and 3.2 years on the return trip, still totaling 30. And again, here's the abridged form with calculations. With that, we've confirmed that we get the same result in 3 different reference frames. And if you're curious about the question marks, their values weren't all that relevant to the example, but here's what they equal. If we isolate Botan's column though, we can notice something interesting. In her own reference frame, she's 25 at the time of the transfer, but in Mary's reference frame, she's 23.2 at the time, and in RCM4's, she's 26.8 at that time. And this corresponds perfectly with the predictions from relativity of simultaneity. This raises an interesting question though. Starting with one perspective and then switching halfway through may not be a single inertial reference frame, but what if Mary were to transfer her consciousness or something? What would she actually see? Well, her perspective would have Botan aging 3.2 years, followed by a sudden jump to a reference frame in which Botan's already 26.8, and then finally Botan aging another 3.2 years. But remember, in relativity, we don't see things in real time, so this only refers to Botan's calculated age. What Mary would actually see is Botan very slowly aging 2 years on the outbound trip, followed by her very quickly aging 8 years on the return trip. And this is simply by virtue of when the light from Botan actually reaches Mary/RCM4. Her actual age can only be calculated by retroactively applying the finite speed of light to this data. Anyway, now we're actually going to return to the acceleration version from earlier. You may have wondered what would happen if the time it takes to turn around was made arbitrarily short. Well, now we have the answer. In the limiting case, Mary's perspective would have Botan going from 23.2 to 26.8 in an instant. That makes this hypothetical scenario pretty much equivalent to the inertial version. Instantaneous changes like this might not be possible in real life, but the fact that we get this equivalence shows that we technically didn't need the acceleration in order to formulate and resolve the paradox. It's for this reason that some people declare the twin paradox has absolutely nothing to do with acceleration. In my opinion, this is kind of a debate on semantics. It's not the acceleration per se that resolves the paradox, but the fact that the outbound and return trips are in different reference frames. This sentence is what really reconciled the two versions for me and provided a fuller understanding. It doesn't matter if you achieve this change in reference frame through acceleration, through a data transfer, or even through the power of the hypothetical, the result is always going to be the same.